All right, well, this is the first of 7 sessions which are going to introduce you to the basics of radiosurgery. And we're going to start this morning by reviewing the history of radiosurgery. Now, a lot of things had to occur before radiosurgery even became technologically possible. And they've occurred really over the past 100 years, so it's like neurosurgery, a fairly new part of medicine. But the first era is basically the first half of the 20th century. And during that period of time, we saw in rapid succession the discovery of X-rays, radiation, radium, cyclotrons, linear accelerators, and Cobalt-60. Wilhelm Conrad Röntgen discovered X-rays accidentally because he had some photographic film in a room with a cathode ray tube and saw that it was exposed. It was only a year later that X-rays were being used to treat skin cancer. And that year, Becquerel basically discovered the principle of radioactivity. Marie and Pierre Curie discovered radium in 1898. And Becquerel and the Curies both wound up winning the Nobel Prize in Physics. And then Marie Curie won a second Nobel Prize, this time in chemistry, in 1911. Both X-rays and radium were used by early neurosurgeons, including Harvey Cushing. So here's Röntgen, who discovered the 3 basic types of radiation: alpha particles, beta particles, and gamma rays, for which he was awarded the Nobel Prize in Physics. And immediately after, he discovered that his photographic emulsion had detected some heretofore undiscovered ray. He called his wife in and had her put her hand in between the cathode ray tube and the film, and there's a famous picture of her hand and the first X-ray with her wedding ring on the hand. On the left is Becquerel, and then we have Marie Curie and Pierre Curie. Marie and Pierre both suffered from radiation toxicity as a result of their experiments. The way they got radium was they worked through tons of uranium ore called pitchblende, using a chemical extraction process to get a very, very small quantity of this extremely radioactive element. Pierre Curie became gradually weaker and weaker and was killed in a carriage accident, but probably because he was sort of disoriented and stumbled in front of a carriage. Now here is a picture from a paper published by Mike Schulder, and it's his review of Harvey Cushing's use of radium in the brachytherapy of brain tumors. And this object here is a metal cylinder containing radium. It's called a radium bomb in a tumor bed. So it's probably the earliest example of brain tumor radiosurgery. And this is Cushing's drawing on one of his 4 cases. He didn't think it helped very much, and so that was the end of brachytherapy for a good while. Here is a body radium bomb from 1924, and you can see there are 3 applicators, and they're all sort of hooked up to an arc, and they're focused so that all 3 beams will come together at the target point. Here is a 13-source radium bomb that sort of looks like the gamma knife. I mean, you've got these 13 sources. Here's the head. This is the back of the patient's head and neck. And all 13 sources are sort of focused and lined up so that the radium beams come together at the focal point, which, of course, is the basic idea of the gamma knife. And that's 1925. So the next important invention was, and now that was is due to the genius of another Nobel Prize winner, Ernest Lawrence, who developed the first model of a cyclotron in 1931. He patented his idea in 1934, and then he opened a lab at UC Berkeley, which subsequently has always been known as the Lawrence Berkeley Lab, where he served as director until his death. He won the Nobel Prize, and he played a major role in the Manhattan Project during World War II. Cyclotrons accelerate charged particles by using high-frequency alternating voltages across D-shaped electrodes, which are called the Ds. And then a perpendicular magnetic field causes the particles to spiral in a circle, so they re-encounter the accelerating voltage many times. Now, originally they were used for high-energy physics research, but today they are used primarily for cancer treatment in proton beam particle accelerators and in the manufacture of isotopes for PET scanning. The advantage of a cyclotron, well, in 1920 it wasn't possible to build a linear accelerator, and because it's round, it can be very compact, which reduces other costs like foundation shielding, building power, etc. But the big disadvantage is that it has a limited capability for accelerating particles. So this is the original Berkeley drawing. These are the D-shaped electrodes, and these are in a museum the actual original Ds that were used in the pioneering cyclotron. And then this is a beam of radiation in a cyclotron, and that blue color is called Cherenkov radiation, and for reasons that only Frank Bova can explain in this room, Cherenkov radiation occurs when when particles travel faster than light can travel in a given medium. Nothing can travel faster than light in a vacuum, but in certain other media, you can get particles that move faster than light, and then you get this blue beam. All right, now that brings us up to the story of the linear accelerator. Linear accelerators accelerate charged subatomic particles by subjecting the particles to oscillating electrical potentials along a linear beam line, and this was first conceived in 1928 by Rolf Widerøe. In 1938, working at Stanford, William Hansen described the concept of accelerating electrons by passing them repeatedly through a resonant microwave cavity. Microwave radiation used to accelerate the particles, and he called his device the Rhumbatron. Now, two critical inventions were needed to develop modern linear accelerators. One of them is called the Magnetron, which was invented by Randall and Boot, and the details of exactly how they work are probably not important, but it's a magnetron, it's a microwave system for accelerating electrons. The most common application of a magnetron today is in your microwave oven. Okay, each microwave has a magnetron, and if your microwave stops heating, it's probably because the magnetron is fried. But you really don't want to get in there and try to fix it yourself, because you might wind up giving yourself a very high dose of microwave energy application. It's also used in radar, and we'll get back to that. This is what a cross-section of a magnetron looks like, and here's an actual magnetron cut in half. The other invention is called the klystron, and klystron amplifiers have the advantage over the magnetron of amplifying a reference signal so the output can be precisely controlled. And this was invented by Russell and Sigurd Varian. You may recognize the name Varian from the brand name for the most commonly found linear accelerator in the world today. They built on Hansen's Rhumbatron work, and their device was ready to roll in 1939, right around the start of World War II. And importantly, During the war, the Axis powers used Cyclotron-based radar, which was then low-powered, and the Allies used Magnetron-based radar, which was much more powerful and accurate and absolutely decisive in the Battle of Britain, which the English really won because they could see the Axis planes coming, knew where they were going, and could intercept them. Now, this is a diagram of a klystron. The electron beam is injected into a resonant cavity. The beam is accelerated and made to travel through a cylindrical tube. The velocity is modulated by a radio frequency signal, and that bunches up the electrons, which are then collected and shot in whatever direction you choose. So one final term that you may run into when you're looking at linear accelerator radiation, although it could apply to all kinds of radiation, the term is Bremsstrahlung, which means breaking radiation, and it refers to any radiation due to the acceleration of a charged particle. It's actually when the particle slows down, the breaking, that the photon is emitted, but most frequently for us it refers to the photon radiation produced by an electron stopping, breaking, in the target end of the linear accelerator, which is usually a tungsten alloy. Modern linear accelerators were developed using this World War II technology, the Clystrons and the Magnetrons at Stanford in 48 and in England in 53. And the first isocentric linear accelerator, that is a linear accelerator that rotated around a point so that the radiation was always focused on that point, was developed in 1960 by Varian. So here is a early non-isocentric linear accelerator. And here is a cross-section diagram of a linear accelerator Varian model from about 10 years ago. But the bottom line is, using microwaves, electrons are accelerated. In this model, they are turned a couple of times, and then they collide in the head of the linear accelerator with a heavy metal. Most of the energy of that collision is heat, but a small percentage is Bremsstrahlung photons, and those photons are collimated and they are aimed at the patient. What about nuclear reactors? The concept of a nuclear chain reaction was first conceived by Leo Szilard in 1933. The first reactor to achieve criticality was Chicago Pile 1, December 2nd, 1940. A group led by Enrico Fermi and Einstein and others recognized the military application. This led to the biggest engineering project in the history of Western civilization, the Manhattan Project, and ultimately the atomic bomb. The first peaceful nuclear power plant was opened in Sellafield, England in 1956. Now, we've been talking about radium, remember, is that original isotope, but because of the development of cyclotrons and nuclear reactors, it became possible to create other kinds of isotopes, even isotopes that would not be found in nature, such as Cobalt-60. Cobalt-60 is produced artificially by neutron bombardment of Cobalt-59, and Cobalt-60 decays to nickel-60. The activated nickel atom emits two gamma rays, and the important thing here is that the two energies are virtually the same energy, 1.17 and 1.13 million electron volts, so it's a very homogeneous emitter of gamma rays. So it has advantages over radium. So it has much softer beta radiation, so it's much easier to shield. It has, as I just said, homogeneous gamma emission. Radium decays partially to radon, which is bad. It's one of the more common environmental causes of cancer. Breakage of a cobalt source is very difficult. Cobalt is relatively inexpensive and can be generated in a reactor in any desired quantity. So cobalt hasn't completely replaced radium in terms of radiation therapy applications, but has largely replaced it, except for a few brachytherapy indications. So cobalt was first produced in 1941 by Livengood and Seaborg using a cyclotron. The first telecobalt machine was loaded in 1951, and by 1961 there were over 1,000 cobalt units around the world, and they were the principal machine for conventional radiotherapy until they were replaced, almost entirely replaced, at least in this country, by linear accelerators. All right, so this is an early cobalt unit. So, obviously a lot of other technology was needed to jump to radiosurgery, which we don't have time to review this morning. The development of computer technology, which is a really interesting story. The development of stereotactic frames, which occurred over about the same time period, starting in the late 1800s and moving forward. And of course modern medical imaging, CT, MR, and PET, none of which existed when I went to medical school, so it hasn't been that long ago. Okay, so from 1950 on, the second half of the 20th century, we're now entering what I think we could call the radiosurgical era. And it really has three chapters: the gamma knife Lexile chapter, the particle beam chapter, and the linear accelerator chapter. So Lexile was born in 1907 in Sweden. He went to medical school in Stockholm. He became professor of neurosurgery in Lund in 1958, and then in 1960 he became a professor of neurosurgery at the Karolinska, succeeding his teacher and a very famous neurosurgeon at that time, Herbert Oliver-Krone. He remained professor until 1974. He died in January of 1986 in Switzerland. So, why did Lexile decide to develop a radiosurgical system where none had really existed before? Here are a few of his quotes. So that the school of Oliver-Krone was hard. The trade could not be done better in any other place, but sometimes even his mastership did not suffice. Progress goes over heaps of corpses, said the great surgeon von Mikulicz, but it was difficult to accept the high mortality and the failures fastened in my mind. Then he tells a story about a little Jewish boy from Warsaw, and he was administering the anesthetic while Oliver-Krone was doing the operation, and coagulation, suck, I mean, that, nothing changes, right? It seemed the bleeding could not be stopped. The boy started to breathe more and more superficially and then stopped breathing altogether. And after changing, I went through the park and saw the father, a rabbi. I greeted him, but did not dare to go and tell him what had happened. The results of open surgery were very poor, so it stimulated Lexile to try to develop an alternative. He had many, many accomplishments in addition to the invention of the gamma knife. He probably should have won the Nobel Prize in Physiology for discovering the gamma motor neuronal system as part of his PhD thesis. We all use the Lexile rongeurs in surgery every day. The Lexile stereotactic frame has become the prototype of all modern stereotactic frames. There are different kinds historically, but all the modern frames are arc-centered, which is his concept. He developed aqueductal stenosis stenting, which has had a recent resurgence. And he also developed the pallidotomy for Parkinson's disease, which was lost for a couple of decades, then rediscovered by Lori Lightnin. It's been put back on the shelf again, really, because of DBS, but it remains a good operation. And these are a few of his inventions. In 1951, he developed the idea of radiosurgery, and he coined the term. And while still at the University of Lund, using relatively low energy X-rays, he treated patients for trigeminal neuralgia. He then worked with Larson using the Uppsala University Cyclotron to do proton beam radiosurgery. and then finally with Leiden actually proposed the use of linear accelerators. If radiation surgery will reach a position as a standard procedure, improved electron accelerators for Röntgen production adapted for the purpose would seem a most attractive alternative. But they discarded the linear accelerator idea because back then the linear accelerators weren't even isocentric, let alone accurate enough to do radiosurgery. So they proceeded to develop the gamma knife. The first unit was constructed at the Motala Verkstad, which is the oldest factory in Sweden. Frank and I actually took a train down from Stockholm and had lunch there with the workers. It had 179 cobalt sources. It was intended to produce elliptical lesions for functional neurosurgery. And they actually treated the first patient at the factory in 1967, and they moved it to a small hospital in Stockholm called the Sophia Hemmet, and then that unit was moved to UCLA. In 1982, it still exists at UCLA. It hasn't been reloaded, so the Cobalt has gone through many, many, many half-lives, but it was used to treat a few patients at UCLA. In 1974, the original Karolinski unit went in, and it was designed to produce spherical lesions that were more appropriate for anatomical lesions. And then in the 80s, units were installed in Buenos Aires, Sheffield, Pittsburgh, and Charlottesville. And this is the unit that Frank and I looked at in Stockholm in 1986. This is an advertisement that I think nicely shows the principle of those 201 cobalt beams all going through different areas of normal brain but coming together at the target. So the target gets a high dose of radiation, the normal brain gets a low dose. Now the latest gamma knife unit is called the Perfection. It has 192 cobalt sources. It has a number of engineering improvements, including internal collimation, automatic beam blocking, and a larger working volume. This is what the unit looks like externally. These are some cutaway diagrams that explain how all of the automation works inside the machine. So a few more words from Lexile's writings, and then we'll move on to the next chapter. The bloodless radio knife with Cobalt-60 has been perfected. It's quite simple, but no instrument is better than the hand that holds it. Fools with tools are still fools. Balancing between knowledge, experience, and necessary innovation, it is the patient who still takes all of the risks. And finally, and I really love this one because it reminds me of morning conference, I go to the meeting room to discuss the treatment of vascular malformations. Now there exist many new surgical alternatives. The knife, the surgeon's instrument par excellence, should not be used in the brain. Cushing understood this when he started to use radiofrequency, the Bova unit, to cut and to stop the bleeding. Surgery has to make use of the possibilities provided by modern physics and technology. There is still a lot to be done. All right, the particle beam chapter. The possibility of using particle beams for medical applications was first suggested by Robert Wilson while he was designing the original Harvard Cyclotron laboratory. And the first medical particle beam treatments were performed at facilities that were originally built for physics research. So remember the Lawrence Berkeley lab, where it was used for pituitary irradiation in metastatic breast cancer. The Gustav Werner Institute with Larson and Lexile, I've already mentioned. But the big breakthrough came when the Harvard Cyclotron and Massachusetts General Hospital started a collaboration in 1961. Over 9,000 patients were eventually treated before shutdown of the Harvard Cyclotron lab in 2002, and most of them were treated by a neurosurgeon called Ray Gelberg. The Loma Linda Proton Beam Center was the first center built specifically for medical applications alone. It opened in 1990. The Harvard Cyclotron was replaced by the Northeast Proton Center at MGH in 2001. And as of a year ago, there were 29 proton beam therapy centers up and running around the world. Now, the big deal with particle beam is the Bragg peak. So photons, their energy from a linear accelerator or gamma knife exponentially decays as it goes through tissue. So we get the radiosurgical effect by intersecting multiple photon beams. Proton beams or helium beams, the energy increases and then stops. So there is no exit dose. And I think you can all see how no exit dose is theoretically advantageous. So here is John Lawrence, who's Ernest's brother, who was a pioneer in nuclear medicine. He used the Berkeley cyclotron for metastatic breast cancer. As I mentioned, Larson and Lexile, here they are using the proton beam unit at Uppsala, but they rejected it as too complicated. And the Harvard Cyclotron lab treated 9,000 patients over 9,000 before shutdown. Here is Robert Wilson at groundbreaking for one of the laboratories. And here is Ray Gelberg, a very young Ray Gelberg, applying a stereotactic frame for proton beam treatment at the Harvard Cyclotron. Jacob Fabricant was a radiologist who joined the UC Berkeley group, and he was a pioneer in the use of a different kind of particle beam, helium beams, for the treatment of arteriovenous malformations. Now, this is the particle beam facility run by the University of Florida in Jacksonville. So this is the cyclotron. And remember, the advantage of the cyclotron is that they don't take up very much space, relatively speaking. These are the beam pathways out of the and connecting to each of the treatment rooms. Here's an actual treatment room. Here's where the beam comes out. Why particle beams? Well, there are some tumors where particle beam treatment has produced some pretty good results. Uveal melanomas, chondrosarcomas and chordomas, and unresectable sarcomas. Now, I would argue that, and I think most people would agree that, the reason that the results are good is simply that they've managed to attract the largest number of patients and they've figured out a good treatment protocol, which could be reproduced by a photon unit. But nonetheless, the best results reported in the literature are from particle beam units in these groups. There's also a pretty strong feeling that because of the no exit dose, that if used to treat pediatric neoplasms, that there might be a reduced incidence of subsequent radiation-induced malignancies. And it's very, very popular for prostate cancer right now. It is a very expensive technology. It'll cost you about $150 million to get a particle beam unit up and running. But people are doing it because you get paid a lot more if you treat somebody with particle beams than if you treat them with photons. So this is a review of all of 243 studies in the literature. And I'll just conclude the particle beam chapter by saying no comparative study reported statistically significant or important differences in overall or cancer-specific survival or in total serious adverse effects. But nonetheless, this is a technology that is expanding, and you're all going to see it in the course of your careers as neurosurgeons. Now, the third chapter is the linear accelerator radiosurgery chapter. The first application of a linear accelerator to radiosurgery was by Betty and Derachinsky in Buenos Aires in 1983, and then by Colombo and Avanzo in Vicenza, and then Hartmann in Heidelberg, all in the early to mid-1980s. Here is Betty's original paper in neurosurgery. And this is his unit, and in this unit, the patient sits in a chair. The beam is stationary and the chair rotates. This is the Colombo paper, and this looks a little bit more like the kind of radiosurgery that we do, multiple intersecting arcs of radiation, and we'll talk more about that as the week goes on. Other people improve these systems. Erwin Podgorczak came up with a system that simultaneously rotated the couch and the gantry. Winston and Lutz did breakthrough work in measuring the accuracy of linear accelerators, and then I persuaded Dr. Bova and explained to him how we could convert a linear accelerator into a much more accurate device back in the 90s. And Radionics produced the first commercial Linac system. This should be 89, by the way. First commercial Linac system in 1990. So here is Erwin Podgorczak, and this is Danny Lexile, Lars's son, and Hans Jürgen, I think his name is, a physicist from Stockholm. Here's the Winston Lutz paper, which is important because they came up with this floor stand, and they came up with a method of using a phantom and radiographs to measure and improve, hopefully, the accuracy of linear accelerator. This is Ken Winston, who's a pediatric neurosurgeon. He was at Harvard at that time, but now he's at the University of Colorado. Wendell Lutz, at the time, was a physicist there as well. This is our paper from 1989 in surgical neurology. We thought it was a pretty big deal. It took us 2 years, a lot of sweat equity to invent this thing. And I submitted the paper to a Journal of Neurosurgery, and the editor wrote me back and he said, "This isn't neurosurgery. Try a radiation oncology journal." So we were able to get it published in Surgical Neurology. Of course, you cannot pick up a neurosurgical journal today without at least 1 or 2 papers talking about radiosurgery. But back then, it was strictly verboten. And here is our original system, where Frank really built this system of bearings that replaced the inaccurate bearings inherent to the couch and the gantry of the linear. This you may have seen before, but this is actually Frank and me treating our first patient in 1981. And notice Bova's thin back then. This is another patient that we treated some years later, but this girl was a star volleyball player in high school because she was a pituitary giant. And Al Roten had operated on her several times, but couldn't get the tumor completely out because it went into the cavernous sinus, and we treated her. She was 6'11". So coming up to current linear accelerator technology, almost all of the modern systems have some kind of image guidance incorporated into the system. Ours has an onboard CT scanner. Others use stereoscopic kilovoltage X-rays like the CyberKnife, or optical tracking devices. And there are multiple approaches to using linear accelerators for beam shaping and dose planning. Sphere packing is what we use. Micro multileaf and intensity modulation are several others that we'll discuss later. This is the original radionic system, the first commercial system. This is the system that we use today, the Varian Trilogy system, which has all of the University of Florida patented hardware and software for radiosurgery, and the onboard CT scanner. This is a tomotherapy device. This is the Novalis system, which is made by Brainlab. This is the CyberKnife. There's a CyberKnife at North Florida. This part of the CyberKnife is a linear accelerator. It's a miniature linear accelerator that's on a robotic arm. And this is the GE Synergy machine, which is over at the Cancer Center. It's, the Electa Synergy machine, and it's very similar to the Trilogy machine. So I mentioned sphere packing. Sphere packing is a dose planning method where you put a sphere of radiation into the biggest sphere that you can fit into the tumor. And then you put the next biggest sphere and next biggest and so on, using very tiny spheres so that you get a composite radiation shape that precisely matches the shape of this very non-spherical tumor. It's conformal. Another approach is to use multiple fixed beams of radiation. Another approach is to use this device. This is a micro multileaf. This is an old one The newer ones have more leaves and they're smaller, but they're driven by computer in and out so that you can get a beam's eye shape of the micromultileaf that matches the shape of the lesion from that particular view. And you can, using the sphere packing or multileaf, you can get very similar looking dose. Here, for example, is a micromultileaf generated plan for spinal radiotherapy. So that brings us to the latest, greatest area of radiosurgery, which is stereotactic body radiosurgery, which was first proposed by Lax and Blomgren at the Karolinska Institute in 1991, and they designed a body immobilization frame that was later produced by Ellipta. At the same time, Uematsu in Japan reported his results using radiosurgery to treat lung cancer. The first extension to the spine was published by Hamilton and Bruce Lulu from the University of Arizona. Timmerman from Indiana has published very promising results for lung tumors, and Wolf likewise on hepatic tumors. So here is the original Hamilton-Lulu. This was an invasive frame that used clamps through small incisions that clamped onto the spinous process. Then a localizer was put onto this. The radiographic localization and planning were done, and then the beams of radiation were delivered. So what are the issues taking radiosurgery out of the head and applying it elsewhere in the body? Well, the main issue is organ motion. We don't have to worry about that with the brain inside the cranium. But anywhere else in the body, we've either got to dampen the organ motion, which you can do by squeezing on the patient in a frame or having them breath hold while you deliver a treatment, or doing it under general anesthesia and oxygenating them and then just stopping the respiration during the delivery of treatment. Or you can gate, that is, you can image the organ as it's moving, say using ultrasound, and you only deliver the beam when the target is within a defined area, that's gating. Or you can chase, you can determine the motion of the organ, and you can develop a beam chasing algorithm that will follow the organ. So lacking a stereotactic frame that patients will accept for the body, onboard imaging must be used for body radiosurgery. And cone beam CT scan, basically, is used for Varian, Ellipta, Siemens, and Encore and tomotherapy. Orthogonal X-rays with bony landmarks or implanted fiducials is used in the CyberKnife. And that's why the CyberKnife, for all the excellent marketing and publicity, it's an outmoded technology. I mean, which is better for localizing, plain X-rays or CAT scan? Okay, so the most common indications for body radiosurgery are non-metastatic primary cancers and oligometastatic disease. And by oligo, I mean patients with metastatic cancer that only have a few mets. SBRT has been used to treat lung, liver, prostate, kidney, and pancreatic primary tumors. It has been used to treat oligometastatic disease in the lung, liver, and spine. Phase 1 and 2 trials have demonstrated feasibility and efficacy. Most trials have relatively short follow-up, and prospective randomized trials with longer follow-up are in progress and will. I'm going to go through this very rapidly. These are you can get them in more detail if you wish online, but are some results from the literature. Early stage non-small cell lung cancer. Look at these local control rates: 80%, 80%, 98%. 92% at 3 years. So the idea now is that if you can catch a lung cancer before it spreads to the lymph nodes and fry it with much higher doses of radiation than could be delivered conventionally, because you'd hurt the normal lung, you can cure them. And here's an example of a lung cancer with what should look familiar to you, just a normal radiosurgical field. And this dose of radiation here would be something like 90 gray. I mean, an enormous dose of radiation compared to what could be given with conventional radiotherapy techniques. Here is pancreatic cancer, a horrible cancer, mainly because when we detect it, it's already metastasized. But if you can get it before it metastasizes, again, the local control rates are very high, and that beats a Whipple procedure, probably. And here's spinal mets, and there are a lot of studies. I think Peter Gersden has done the best work for spinal mets, but the local control rate for spine mets is spectacular with radiosurgery, and the pain relief is very, very good. So if the patient's spine is unstable, they need surgery. But if they've got a stable spine, they can just be treated with radiosurgery if the cord isn't compressed. And if they're unstable, sometimes they can be treated with a vertebroplasty and then radiosurgery instead of much more aggressive surgical approaches. And these are liver mets. You know, there is no good treatment really for liver mets. They can freeze them, they can fry them with probes. Sometimes they can resect part of the liver, but this is a breakthrough treatment for liver mets, oligometastatic liver disease. So let's summarize here, because I think the story is quite interesting. The radiation therapy, that first half of the 20th century, began as the result of breakthrough physics research, and many of those physicists won Nobel Prizes for their work. Modern techniques that we now use today for delivering radiation therapy were refined using technology that was developed during World War II. Radiosurgery began as a cutting-edge technology developed by neurosurgeons and physicists. And as the technologies matured, it has become an accepted and practical tool for many neurosurgical diseases. And the radiosurgical paradigm has now been adopted by a lot of other people. Radiation oncology is finally on board with it, just now. Urologists, thoracic surgeons, and others are now using it as a cutting-edge treatment for diseases elsewhere in the body. So this is a great book by Malcolm Gladwell. It's a quick read, and I would encourage all of you to look. But he maybe helps us understand how innovation occurs. And he gives the example of hybrid seed corn, which was introduced in the 1930s. And initially, only a handful adopted the new seed. They're called the innovators. And then a little bit later, the early adopters. And then they were followed by the early and the late majority, and finally the laggards. Okay? And the innovators and the early adopters are visionaries. And for the rest, risk is a very negative word. The attitudes of the early adopters of new technology versus the others are fundamentally incompatible. And this resonates with the Dreyfus learning model. Those who are competent follow the rules masterfully, but those who are masters break the rules. The original radiosurgeons regularly broke the rules, and by doing so, they created a new paradigm for brain treatments. And then this book has been called the greatest book written in the 20th century, The Structure of Scientific Revolutions, by Thomas, who's a historian. The term paradigm shift, which is in common usage today, was coined by Thomas Kuhn in his book in 1962. And he used it to describe a revolution which occurs when scientists encounter anomalies which cannot be explained by the currently accepted paradigm. After a crisis period, a new paradigm is adopted, and the new paradigm is always better, not just different. So here are some paradigm shifts. Ptolemaic cosmology to Copernican cosmology. Biogenesis versus spontaneous generation. Newtonian physics overcome by Einsteinian relativistic physics and quantum mechanics. Quantum mechanics versus classical mechanics. Darwin's theory of natural selection. The sexual revolution, some of us lived through that one. And radiosurgery. is a paradigm shift. I'd just like to conclude my history of the development of radiosurgery by reminding you that the great thing about radiosurgery is that although it is performed by a team, neurosurgeon, physicist, and radiation oncologist, the neurosurgeon is always right. Thank you.